this is k times ct, that's k times ct. This is k squared times ct, so k squared times ct must equal this, which is ct equals d plus d. Okay, so that's crucial. So it tells us that ct plus d plus d is equal to this thing, k squared times ct. Okay, so we will call this equation 2 prime. Now, if you compare with what we had before, when we made the assumption that of universal time, so we simply assumed that this distance was the same as this, or this amount of time was the same as that amount of time, we got some equation for k. I'll just remind you what that equation was. We called it equation 2. It was ct plus d equals k ct. Okay, so this was our equation 2, which was based on universal time. This is based on principle P1. Okay, so notice that there's some similarity here. Ct, instead of ct plus 2d, we have ct plus d here. Instead of a k squared ct, we have a k ct. That's a square, that's not a square. Okay, so there's a difference here. We're going to get a different value of k.
Are you doing that in this one first right now?
Yep.
How does that happen for the other signal? How does that happen for the satellite signal in the other right left?
You've heard of it. But this amount of t is order. Suppose that we've got Bob is drifting past like this. They zero the clock, Alice waits on t, sends the signal. If she waits 5 seconds and sends the signal out, and then it stops that clock, so when we get the reading, she'll get the value for k over. Right? That's what we're getting. This is here. Okay. The vertical thing. That's ct right there. So like that's the ct we're using right there, right? And so we're using that time. We're using that time in the over there. So are we saying that the same time happens for both observers? No. So are those T's different? Those T's are different. Yeah. The capital T over here refers to the time of Alice, and that Alice waits. The capital T refers to the time of Bob waits, and they need not be the same. Okay, so I'm going to call them different names, but then we're going to talk to you next year. Yeah, good point. Okay, so we have these two equations, and we also had, recall equation 1. Does anyone recall equation 1? Oops, I don't have it down here. What's equation 1? Okay, hang on. What is it? D over ct equals, d over c, 1 minus d over c. Okay, so equation number 1 is true regardless. Equation number 1 is trivial. Okay, there's no physics in it. Okay, equation number 2 or 2 prime, here's where all the physics lies. If we assume universal time, we get this. If we assume principle T1, we get that. Okay, so when we combine equation number 1 with equation number 2, we got the non-relativistic Doppler shift. Okay, now we're going to combine equation 1 with 2 prime, and we'll find a new way of determining k, and I'll leave the algebra to you. If you combine these two equations together and solve for k, you get k is equal to a square root, because there's a square there, you get a square root of 1 plus d over c divided by 1 minus d over c. Okay? And that factor of k is a Doppler shift in exactly, or 1 over k actually, is a Doppler shift in exactly the same way that we had the Doppler shift for sound in air. Okay, so this is called the relativistic Doppler shift. So I'm not going to talk about that, because you have an exercise which will give you some examples and familiarity with working with this Doppler shift and see what the results are. But basically, if Bob is drifting away from Alice, she has a light signal, let's say a laser, say a green laser that's shining toward Bob. If Bob is drifting away, she will see that laser light redshifted towards the frequency lowered, so redshifted, so the light will be redder. If Bob is moving toward Alice, he will see that green light shifted towards the blue. Okay, so just like a sine line coming toward or away from you, it's higher, lower, same thing applies for light. But for light, the Doppler shift is slightly different. What I want you to notice about this Doppler shift is, well, in the case of the non-relativistic Doppler shift was this, 1 over 1 minus v over c. And for this guy, so the Doppler shift 1 over k, okay, just getting messy, 1 over k is 1 minus d over c. Okay, so remember, for the non-relativistic Doppler shift, we could consider the possibility that Bob was moving supersonic, okay, moving it faster than the speed of sound. We could easily put into this equation a v greater than c, in which case he hears the thing backwards, right? Have we talked about that? Okay, what happens if we put a v bigger than c in this equation? You can't, because or negative. If I put a d bigger than c here, let's put a d equals 2 times c. Then I'll have a 1 minus 2 is negative 1. Where the numerator was positive, I'll have a negative number under the square root, and then we'll get an imaginary Doppler shift. So I can't have that. So right away, built into this Doppler shift is the idea that Bob has more faster than the speed of light. Okay, so, etc. So there are exercises on this. So I want you to, I think you'll have a lot of fun doing those exercises. Okay, so let's just leave it at that. So sure, relativistic Doppler shift. This is very, very important. This is how we measure velocities of things. Right? If people want to measure the velocity of a galaxy, well, I can't go out there with a big meter stick and a clock and say, yes, this galaxy is moving across my meter stick at a certain rate, right? I mean, it's going to be more practical than that. And so what we do is we measure. So here's us over here, and here's this galaxy, and this galaxy is, say, drifting away from us. And so the light that's coming to us we say it's emitted by excited atoms, so we know exactly the frequency of that light according to the atom itself. We actually need this relativistic formula instead of this guy. You can show that for small values of d, this is the same as this. Maybe that's an exercise for you to think about using the binomial approximation that Sven told you about yesterday. If you use the binomial approximation, this is the same as that for small d over c. But anyways, I'll leave that to the problems. So, right. The important thing about this case for us is that it tells us something very important about the nature of time. Okay, and we will see that presently. Yeah.
So, like, if we were to measure wouldn't that like give us the incorrect answer if it's accelerating away? If it's accelerating, say it's accelerating away from the river. Then wouldn't that answer not tell anything? Oh, do you mean it? I mean, it's 2 points in space like accelerating away from each other, like space comes accelerating. Same expansion, right? Right. So then, when we read that velocity that we get from the frequency, what is that telling us relative to the fact that we know that? Okay, so let me just make a clarification here. So when we say that, maybe let me say a little different.
So what's actually happening is something like this. So here's us, and here's this galaxy, and the space between us and this galaxy is expanding. And so when a photon is emitted over here, and it's traveling through this space is expanding, and the photon gets stretched, its wavelength gets longer. Okay, and so that's a redshift, which is the same kind of thing as this redshift.
Are we able to different plug in with the you said,
yeah, I was saying get the correct one. Okay, yeah. I think those astronomers know what they're doing. Okay, so, but yeah, good question. Okay, so let's look at the important thing here, which is time dilation. What does this tell us about the nature of time? What does K tell us? Okay, so let's plug in some numbers here. How many want to see some numbers? Only one of you. Oh, great. Okay, so you guys are all like really hardcore theory, aren't you? Okay, so I want to see some numbers. Okay, so here we've got, okay, we're just going to draw the experiment again. So we're going to make sure we've got CT here. So CTA, and Bob is drifting over here, CTD, and here is our experiment. Alice waits some time, and then she sends this light signal over. And when Bob receives that light signal, he is some distance d away from Alice. Okay, so let's put in some numbers here. Here's some velocity v. Let's suppose that v is 4/5 the speed of light. Okay, so what that means is that how would I draw this line graphically? In this picture, well, what I would do is I would go 4 units to the right and 5 units up. So on my graph paper, wherever my graph paper is, I've got these little squares, I would go 4 units to the right, 5 units up, or 8 and 10 or whatever. Okay, and that would give me this line, okay, which is 20 to the left of 45 degrees. Sorry, less than 45 degrees. It's moving south. Okay. But close to the right. And let's suppose that Alice, the Bob drifts by Alice like this, crosses her path at this location. She waits a certain time on her watch before she clicks on her laser. And let's suppose that time is very small, 10 to the minus 8 seconds. Okay, so that tells us that c times this time, that's 3 times 78 meters per second, times 10 to the minus 8 seconds is 3 meters. And remember, space and time are measured in meters. Both are measured in meters. So this time CT here is 3 meters. That's actually this distance. Okay. So 3 meters, that just means how far does light travel in 10 to the minus 8 seconds? Well, 15 times 10 to the minus 8 seconds, it'll travel 3 meters. Okay? That's the time on Alice's watch. Okay, see. Okay, and then she sends this guy out, this is 0.5, etc., etc., what else do we need here? Okay, also, recall the equation number 1 there. So d divided by ct is v over c minus whatever v over c. So, let me see. So, what that tells us is that d is this thing times ct. Okay, so what's this? v over c is 4/5 divided by 1 minus 4/5 times ct. We figured out ct is 3 meters. So what is that? That's 12. Okay, 12 meters. Just trying to wake up your algebra brains. Okay, and so then, and also k is this tiny square root 1 minus 1 plus v over c divided by 1 minus v over c. Okay, so that's the square root of 1 plus 4/5 divided by 1 minus 4/5. So what's that? That was fast. So the square root of 9, which is 3. Okay, so that's what that k factor is. So physically, what does that k factor mean? Well, it means that if Alice is sending light to Bob, so according to Alice, she's sending light at a certain frequency. Bob is drifting away from her at 80% speed of light, 4/5 c. Okay, he's going to measure that light at a lower frequency. How much lower? By a factor of 3. Okay? If she's sending light at 3,000 hertz or whatever, 3,000 times 10 to the whatever hertz, he'll measure it at 1,000 times 10 to the whatever hertz. Okay, so that's the redshift. Okay, and so now what can we do with all that? Well, now we can say, oh, okay, well, we know D is figured out as 12 meters, so this distance is 12 meters. Which means, so Alice waits 10 to the minus 8 seconds, clicks the laser on, it catches up with Bob when he has moved 12 meters away from Alice. Okay, so if we know this is 12 meters, what's that? So this is also 12 meters. Okay, so what is that total time? So that total time is 15 meters. There they are. So 3 meters plus 12 meters is 15 meters. So it's 16 meters elapsed on Alice's clock. But how do we convert meters into elapsed time? So the time elapsed on Alice's clock, delta always needs change. So the change in the time elapsed on the time of Alice's clock, the elapsed time is 15 meters. And what do I do? Divide by C. Okay, so what is that? C is 3 times 10 to the 8. We got a 3. 5. 15 over 3 is 5. A 10 to the 8 down here means a 10 to the minus 8 is numerator. Seconds. So remember that Alice waited 10 to the minus 8 seconds. And the elapsed time, and then as you send that light signal out, it was reflected back. The total time is 5 times 10 to the minus 8, so 5 times as long. Okay, and also, what we want here is this guy here, KCT. That's the time elapsed for Bob. Okay, so that's the important one here. Okay, so let's work that out. So K times CT, we just figured out K, that Doppler shift is a factor of 3, and we figured out CT is just 3 meters. So that's 9 meters. Okay, and that tells us that the time elapsed on Bob's clock, from the moment that he crosses Alice's path to the moment that he receives the light signal from Alice, is 9 meters divided by C, which is what? 3. Okay, so let's draw a picture of this. So here's Alice. Here's Bob. So just a simplified picture here. And let me see. The total time for Alice is 5. Let's just drop the 10 to the minus 8. The total time for Alice is 5. And so here she zeroes her clock here. At 1, she emits the light signal, and then it comes back. 2, 3, 4, 5. So 1, 2, 3, 4, 5. So the picture's like this. She emits the light signal, and it comes back. Okay? And for Bob, let's just get rid of that. It's not messy. For Bob, the elapsed time is 3. Okay, so he zeroes his clock here, and it goes 1, 2, 3. Okay? So, when Alice's clock reads 5, Bob's clock reads 3. 5 seconds of elapsed for Alice, or when 5 seconds of elapsed for Alice, only 3 seconds of elapsed for Bob. Okay? So, there's a time division. There's no such thing as universal time. So the picture looks like this. When 1 second elapses for Alice, according to Newtonian time, we just draw horizontal lines like this would correspond to 1 second elapsed for Bob. But from this picture, how much time is actually elapsed for Bob? Is it less or more than 1 second? What is it exactly? Sorry? Take this. Take this for a second. Okay, so this is time dilation. Okay. So basically, the whole thing behind all of this is Einstein's attempt to put light on the same footing as matter. To put, yeah, that's it. That's really all it is. Okay, to recognize that, matter can have physical properties like momentum, energy, angular momentum, and all that stuff. Maxwell's equations tell us that light has exactly the same properties. It has momentum, angular momentum, energy. It can carry all of these things as it moves through the vacuum of space. And so Einstein said, well, let's do them on the same footing. That's all he really said. And when you do that, you discover that the only way you can do that is if there are such things as time dilation. Well, one of the consequences of doing that is, or what's required is that you have this time dilation. Okay, so the idea of universal time is just broken here. Okay, so we realize that that's no longer the case. Okay? All right, so let's just do this in general. So here we plug in some numbers. Let's just take 2 minutes here to make this general and come up with a general formula for time dilation. And so one that many of you will have seen before. Okay, so in general, our picture is like this. CTA, CTD, that, and K on CT. And this is Alice's x-axis. This is space according to Alice, time according to Alice, time according to Bob, and all the equivalent stuff. So what we're going to do is change location here. Okay, we're going to recognize that there is a triangle here. We're going to relabel the size of the triangle. We're going to call this side of it here. We're going to call it C times delta CA. This is the time elapsed for Alice, times C, delta CA times C. Okay? This is the time here elapsed for Bob. We're going to call that C times delta CD, delta CD times C. And this is the distance that Bob moves in Alice's space. So that's the change. That's delta SC. Okay, so we have labeled our triangle with those 3 sides. And so we have delta XA, and what is that? That's just E. We have C times delta CD, and what is that? That's just TCT. And C times delta CA is this plus this. Okay, so now you'll notice, and also we're going to use equation number 1. Okay, so we just changed our notation a little bit. Okay, and so what we find is, so what is delta TA? Well, delta TA, all I do is I take this right-hand side and divide by C. So that's T plus D over C. Okay. So that's T plus, what is D divided by C? D divided by C is what? It's junk times capital T. Okay. And so how do I simplify this? Look at this simplification of that. So, why T? Oh, because we're taking D divided by C. So D divided by C is just this part of it. So we bring the T over to that side. So when I add this to this, how does it simplify? Factor out the T, and then what do I get? And what does this simplify to? Okay, so it simplifies to that. And so let's take the ratio. Physics are almost always just interested in ratios. One time relative to another time, and so on. And so the ratio of delta CD, delta CD to A, the ratio of those two, let's see, what is delta CD? Delta CD is what? Just KT. I just cancel off the C's, right? That's just KT. And delta TA we have is 1 over 1 minus D over C times T. If C cancels out. Okay? So the result we're going to get is independent of how long Alice and Bob waits. Okay? That's just the universal result, the universal relationship between those two servers. Okay, so what is K? Well, let's see, K was, so okay, 1 over this, we move the numerator, becomes 1 minus D over C. So that's that part of it. And then we multiply by K. Well, what was K? K was 1 plus D over C divided by 1 minus D over C square root. Okay, so how does this simplify? How does it simplify that? Yeah, so square root. So you got to one plus D over C. Okay. So here I have an object and a square root of an object. So this is the square root of 1 minus D over C. That's the square root of plus D over C. And so if I bring both of these things together under the square root sign, A minus B times A plus B is A squared minus B squared. So I get 1 minus the square. Okay, so the ratio of the two times is this. So at the end of the day, our final result is, okay, so our final result is